This section is Chapter 4, Ionic Compounds. Ionic compounds, or compounds in general, when electrons interact with each other. Let's consider the periodic table. You can think of the periodic table as a map in which on the left portion or the west portion of the periodic table you find metals, and that's indicated here by the elements shown in yellow or gold. Towards the east side or the right side you have nonmetals. The very far right are your noble gases, and they're called noble gases because they're pretty much inert in that they don't react with other elements, very rare. Then you have these elements right here in the diagonal, and they tend to be metals, and right in this border you have the border between the metals and the non-metals, and these elements are called metalloids. In the center right here they're called transition metals. On the bottom it's called rare earth, or the lanthanide series, or the actinide series. What you will find is that the metallic character of elements tend to increase as you go towards the west and the south end portion of the periodic table, whereas the non-metal character of the elements tend to be more pronounced towards the east or the north and the north section of the periodic table. So the main thing about the elements is that they tend to really give up electron or accept electrons, so they have the same number of electrons as a noble gas. That's why noble gases are so inert, because they're so unstable, and so all the elements want to strive towards the noble gases, the closest noble gases. Take for example lithium. Lithium has 3 electrons. The number of protons and the number of electrons for neutral lithium atoms are equal. If it can give up 1 electron, it will have the same number of electrons as helium, and that's the preferred state of lithium. It prefers to give up 1 electron, therefore it has 3 protons and 2 electrons, giving it a net charge of +1. In fact, all the elements in the 1A family tend to give up 1 electron, so they have the same number of electrons as the noble gas. So we call this the +1 or the alkali metals, and they prefer +1 charge. Beryllium, magnesium, calcium, well, they have 2 electrons in their valence shell, so by giving up 2 electrons they'll have the same number of electrons as the noble gas. Take for example magnesium. Magnesium has 12 protons and 12 electrons. By giving up 2 of its electrons, it'll have the same number of electrons as neon. Therefore it'll have 12 protons, 10 electrons, giving it a net charge of +2. In general, the elements that you see in yellow have fixed charges. Aluminum wants to give up 3, zinc, cadmium wants to give up 2, silver wants to give up 1, and these elements here in yellow all will give up 2 electrons or 1 electron. Remember, when you lose an electron you have more protons than electrons now, and so the element becomes positively charged, or cations. Cations are basically elements with deficient electrons, and so they have a net positive charge. On the other hand, if you look at the elements on the right side of the periodic table, look at the noble gases. They don't prefer any charge because they're totally satisfied. But if you look at the elements on the, say, fluorine has 9 electrons and 9 protons. Chlorine has 7 electrons corresponding to its 7 protons. Now if fluorine can pick up 1 more, it'll have the same number of electrons as neon, and so it'll try and do that. It'll try and pull an electron, say from these elements over here, who wants to give up an electron, and fluorine only wants to take 1. It won't take 2 because that would not give it the same number of electrons as the noble gas. Chlorine will pick up 1 as well, because by picking up 1 it'll have 18 electrons, 17 protons, that'll give it a net charge of -1. When elements gain electrons, they become anions, and so that's corresponding to their negative charge. Oxygen is 2 electrons removed from neon. Why do you think it likes to prefer? It prefers a charge of -2. Same with sulfur, same with selenium, same with tellurium. Nitrogen is 5 electrons away from a noble gas. It prefers a -3, as well as phosphorus, as well as arsenic. Now when you get to the metalloids here, it can either give up electrons or gain electrons, and so it depends on what element it's going to bind with. That determines whether it becomes cation or anion. In general, they prefer to share electrons, so neither giving up or gaining, but sharing. So here again are your cations with fixed charges. Group 1, Group 2, zinc, cadmium, silver, and aluminum. Aluminum should be here as well, but it's not shown. Here are your anions with fixed charge. Fluorine, or the chlorine, bromine, iodine, and astatine, that's -1. Oxygen, sulfur, selenium, tellurium, that's -2. Nitrogen, phosphorus, arsenic, that's -3. And then the transition metals, here they will either give up 1, 2, 3, depends on what makes them stable. And so what you need to do in order to figure out how many electrons these elements will give up is figure out how many electrons its partner will accept. If you know, for example, that you have vanadium oxide and oxygen prefers 2, then what you need to do is you need to figure out that vanadium can probably give up 2 electrons and become VO, but these elements tend to give up any number of electrons, and again it depends on what type of chemistry occurs. Now let's go back and talk about matter again. Remember we talked about in chapter 1 or 2 that all matter can be separated as pure substances or mixture. Mixture can be broken down to homogeneous mixture, in which the consistency is uniform, or heterogeneous mixture, in which the consistency is not uniform. Pure substance is a chemical that has a unique property, and that pure substance can be a compound like water or sodium chloride, or an element like an elemental compound like hydrogen gas or iodine. Now we're going to look at compounds more because that's what this chapter is about. Compounds can be broken down into 3 types depending on how the electrons interact. We could have covalent, polar covalent, or ionic. Let's look at this further. Compounds, if electrons is transferred from one chemical to the other, then what we have is ionic compounds. That is, the cation, the metal, will give up in its electron, the non-metal will accept an electron, and then they're attracted to each other through electrostatic interaction or Coulombic attraction. These are called ionic compounds because they form from ions. When the elements do not want to give up electrons or does not want to accept electrons, then they tend to share electrons, and that may be because the element is combining with itself, and so it has equal strength in terms of giving up or accepting electrons. These are called covalent compounds. It's equal sharing of electrons, and these tend to happen to nonmetals. And then when you have unequal sharing of electrons, you have, say, one element that has a greater tendency to pull electrons than the other, then these are called polar covalent because it's not a complete transfer. It's actually unequal sharing of the electrons. And that might happen between, say, a carbon and an oxygen, where you have carbon monoxide, or say nitrogen and an oxygen, whereas you have nitro monoxide. So unequal sharing of electrons are called polar covalent. Before we move on, let's discuss how we represent chemicals. Now, there's a number of ways chemists communicate with them amongst themselves in order to talk the language of chemistry and understand what chemicals they're referring to. So this is chemical nomenclature. First of all, we know about the chemical name. These are word names for chemicals like water. Water is H2O, methane, CH4, salt, table salt, NaCl. Acid, you have sulfuric acid, acetic acid, hydrochloric acid, ammonia, NH3, glucose, sugar, blood sugar, C6H12O12, O6. Okay, those are the names of the chemicals. Now the formula tells you the number, what type of elements are involved, and the number of these elements. Take, for example, NaCl, that's table salt. You've got, for every one sodium, you have a chloride that is attracted to it. Look at glucose, C6H12O6. For every 6 carbons, there are 12 hydrogens and 6 oxygens. Ethanol, for every 2 carbons, there are 6 hydrogens. There's a 5 here, and there's another one here through the OH, and then 1 oxygen. So this is called the chemical formula because they tell you the type of elements and the number of elements. It doesn't tell you anything about the structure, however. Molecular formula are for those chemicals in which the elements share electrons. The elements, like in water, hydrogen and oxygen, they share the electrons between each other. The bonds are formed by covalent bonds. So how do you know if it's a molecular compound? Well, the formula will not have a metal. If there's no metal in the formula, then most likely it's a covalent compound and it's a molecular compound. It's a molecular formula. Now, we can also take that molecular formula and give you a pictorial view of how the atoms are arranged in space. Take, for example, methane, CH4, which we see right here. But if we draw it out, we see that the carbon is attached to 4 hydrogens. It's not 1 carbon and then 4 hydrogens attached to each other. It's 1 carbon surrounded by 4 hydrogens. That's the structural formula. If you want a 3D model, it's this shape right here. It's called a tetrahedral. It's like a pyramid. Carbon's in the center. There's 3 legs on the hydrogen, and then there's an apex here. This right here, well, that happens to be, in this particular case, I believe it is caffeine. And in this particular case, what we have here is a rendering structure showing that these are carbons, these are nitrogens, and these are oxygens, and the small ones are hydrogens. So it gives you a better view of how the atoms are put together in 3-dimensional space. The empirical formula is generally the lowest ratio by which the atoms are written out. Take, for example, glucose. The structure itself, the chemical molecular formula itself, has 6 carbons, 12 hydrogens, and 6 oxygens. But when we do an analysis, generally it doesn't tell us that there are 6 carbons, 12 hydrogens, and 6 oxygen. It only tells us the ratio by which these elements exist. And so that's called the empirical formula. For every 1 carbon, there are 2 hydrogens and 1 oxygen. The empirical formula is always true for ionic compounds, because ionic compounds are always written in terms of the lowest ratio by which they exist. Whenever you write the empirical formula of ionic compounds, it's also called the formula unit. In this particular case, you've got sodium, which is a cation plus 1. And you know it's a plus 1 because it's in the 1A family and it wants to give up 1 electron. And chlorine, which is a negative 1 because it's in the 7A family and it wants to gain electrons. And so what we have here is 1 sodium and 1 chloride interacts with each other. Potassium hydroxide. Potassium's plus 1. Now, we haven't talked about this yet, but OH is what we call a polyatomic anion. It's a cluster of atoms that act as one unit, and it happens to be a negative 1 charge. Here's another polyatomic ion, nitrate, NO3. That operates as one unit, and that has a negative 1 charge. So it takes 1 iron to combine with 2 nitrates, and so the formula, the ionic formula or the formula unit, is Fe parentheses NO3 parentheses 2. So these are the different ways we represent chemical formulas. How are compounds formed? Compounds are generally formed because the electrons are interacting. They're either being transferred or being shared unequally. There are 2 types: covalent, in which electrons are shared, and ionic, in which electrons are transferred. And this plays out because of the octet rule. The octet rule simply states that atoms will transfer or share electrons in order to have the same number of electrons as its closest noble gas. And we alluded to that earlier in this discussion when we talked about the periodic table, that elements want to either give up or gain electrons so that they have the same number of electrons as a noble gas. If it doesn't give up or gain, then they'll share electrons so it has the same number of a noble gas. And this is called the octet rule because elements want to have a full set of 8 electrons in its outermost shell, its valence shell. Covalent compounds are formed by atoms sharing as many electrons needed to obey the octet rule. So let's take a look at a covalent compound like fluorine. Know that fluorine, because it's in the 7A family, has 7 valence electrons. It has 9 protons and 9 total electrons, but the outermost shell, as you see here, there are 7. There's 2 in the inner shell. There's 2, 4, 6, 7. 7 plus 2 is 9. Likewise here in this fluorine atom. So what will happen is that these 2 electrons will come together and be shared. These 2 electrons are going to be counted for each fluorine atom. And by doing so, we now have 8 electrons each in each atom. And that's why we have this covalent compounds, because electrons are not transferred. It's actually shared between the 2 atoms. Now let's take a look at an ionic compound. In this particular case, we'll have sodium and fluorine combining. Now we know that sodium has a total of 2, 4, 6. You can't see it here, but it should have a total of 11 electrons. Okay, there's 2 here and there's 2 here, and there's 1 electron in its valence shell. By giving up that 1 electron, it will now have a full octet because the inner shell now becomes the valence shell, and there will be 8. Fluorine, on the other hand, is 1 electron removed from a valence, from an octet, and so by picking up that 1 electron, it too will have an octet. And so this is the ionic compound that's formed, NaF, sodium fluoride. Atoms will transfer or share electrons in order to have the same number of electrons as its closest noble gas. Let's consider forming compounds from elements. Let's see what happens Again, in this scenario where a metal and a nonmetal combine, let's consider sodium and chloride. Here, sodium has 11 electrons, 1 electron in its valence shell. By giving up that 1 electron, it becomes a cation. Chlorine needs to accept that 1 electron, and so by accepting that 1 electron, it becomes an anion. And so together, they're going to attract each other through electrostatic interaction. There's the electron configuration of how that all works. And what we have here is the electron is sodium chloride forming, NaCl. And this thing is because of the electrostatic attraction between the cation and the anion. This is called the lattice energy. It's what makes the crystal for the sodium chloride compound. Now, sodium chloride crystalline solid is three-dimensional. You have the sodium being attracted to as many chlorine as possible, and the chlorine being attracted to as many sodium as possible in a three-dimensional matrix. These atoms are held together again by lattice energy or electrostatic interaction, and the lattice energy of these ionic compounds can be overcome by taking this chemical and putting it in water, where water will stabilize these ions to a greater degree and therefore separate them, and that's the dissolving process. Here's a illustration of the sodium chloride ionic lattice, and you notice it's positive, negative, or sodium chloride, sodium chloride, sodium chloride, three-dimensional matrix.
Let's look at sodium chloride. This will be our example ionic compound. NaCl does not exist as a single unit like a molecule. This goes for all ionic compounds. So this would not be a valid way to represent sodium chloride. And like any ionic compound, in the solid state, sodium chloride exists as a crystal. So a very tiny crystal would look like this with alternating sodium and chloride. And a little bit of a different view. The formula unit is NaCl, but if we look inside the crystal, the sodium and chloride ions are actually bonded to 6 oppositely charged neighbors. So if we shrink the ions, we can take a better look inside. And it's a little bit hard to see. So what we're going to do is take a look at a particular chloride ion, that one right there, and ask the question, how many sodium ions is the chloride ion close enough to bond with? Let's start with a head-on view first. And as we change the perspective, you can see there are exactly 6 sodium ions that the chloride ions is equidistant and can bond to. If we ask the same question of sodium, how many chloride ions can it bond to? Well, again, there are 6 chloride ions that it's equidistant to, and therefore the sodium ion also bonds to 6 chloride ions. So as you go throughout the crystal, you can see that is always the case. Because each sodium is bonded to more than one chloride ion, and each chloride ion is bonded to more than one sodium ion, then you can think of all the ions in the whole crystal part of one single bonded unit. And the crystal below would be Na32Cl32. So you can imagine that would be very impractical given the enormous numbers of ions in a crystal large enough to see with our eyes. So only the ratio of ions is given, and that would be its empirical formula. But we call the empirical formula of an ionic compound the formula unit. And sodium chloride is the formula unit for the sodium chloride crystal, and it is the smallest whole number ratio of sodium and chloride ions in the crystal. So all formula units are the smallest whole number ratio of the ions in the crystal. That goes for all formula units. Here's another example, calcium fluoride. You've got 1 calcium for every 2 fluorides. The calcium is 2+, the fluoride is 1-. It has a slightly different crystal structure to account for, rather than the 1-to-1 ratio of sodium chloride, you have a 1-to-2 ratio of calcium fluoride. And if we shrink the atoms to take a better look and see how the calcium is connected to the fluorides, you can see that each calcium has 8 nearest fluoride neighbors, and so it is equally bonded to those 8 fluoride neighbors. And if we look at the fluorine, each fluoride has 4 closest calcium neighbors. And again, like sodium chloride, the whole crystal acts as one single bonded unit, and so we need to express the formula as the lowest whole number ratio being CaF2. So what about molecules? How are they different? Let's take a look at water. We've got the space-filling model on the left, ball and stick model on the right. It's covalently bonded hydrogen and oxygen. And a collection of water molecules is just that, a collection of individual units of H2O that are covalently bonded single units of 2 hydrogens and 1 oxygen. They're not connected to each other except by weak forces. And so large amounts of H2O, any interaction between the water molecules due to weak forces, the molecules they still behave as individual units, not one large bonded unit as in an ionic crystal.
So, let's see how covalent compounds are formed. Here's 3 examples. The first example is hydrogen and hydrogen coming together. Hydrogen has 1 valence electrons. Instead of giving up electrons or accepting electrons, they mutually agree to share electrons. In the hydrogen molecule, the 2 overlapping 1s orbital with its 1 electrons overlap, and the electrons are shared between the 2 elements. The electrons spend a great deal of the time between the 2 nuclei of the hydrogen atom, and therefore forms a bond, a single bond. What happens if hydrogen combines with fluorine? So we have HF. That too is a covalent, polar covalent compound. In this particular case, there's 1 electron from the hydrogen in the 1s orbital. Remember that fluorine has 9 electrons, 7 in the valence shell. But if you remember, one of the electrons in the p orbital is unpaired, and so it's that electron that's unpaired in the p orbital. Here, the other p orbitals in the fluorine are left out for simplicity, but one of the electrons can orientate itself so that it overlaps with the 1s orbital in hydrogen, and these 2 electrons between the fluorine and the hydrogens are now shared between the 2, not mutually shared, sort of like unevenly shared. So this is called a polar covalent compound. Again, the electrons spend a great deal of its time between the 2 nucleus of the hydrogen and fluorine atom, and so that's why the bond is formed. Now consider what happens when 2 fluorine combine, and we talked about that earlier. In this particular case, one of the electrons in the p orbital in one fluorine and the other odd electron in the other fluorine in its p orbital overlap, and you form a single bond between the 2 fluorides, and therefore the formula for fluorine is F2. So when we talk about compounds forming, we have covalent compounds, and whenever we have covalent compounds, we don't need to think about the charge. We don't need to think about how many electrons is release or accept. But if we're going to be talking about, say, ionic compounds, then we need to know how many electrons an element will give up and how many electrons an element will accept. And that number of electrons is usually the common charge, or something called the oxidation number. So we can easily predict the common charge of elements because where they lie in the periodic table. There are other elements, however, in which we have to know the partner first before we can predict its oxidation number. 1A elements, that's hydrogen, lithium, sodium, tend to give up 1 electron. They form cation. 2A family, that's the alkaline metal. They tend to have 2 electrons in its valence shell. They tend to form a +2 cation. Elements that are in the 3A, like boron and aluminum, they give up 3 electrons, and so they form the +3 cations. Remember, metals, no matter whether they're alkali, alkaline, transition, lanthanide, actinide, will always be cations because they prefer to give up electrons. Nonmetals, however, will form anions because they don't want to give up electrons, they want to gain electrons. The closest, the B line to the noble gas is gaining electrons. And so halogens, fluorines, chlorines, bromines will pick up 1 electron and become -1. The oxygen family elements, oxygen, sulfur, selenium, are 2 electrons removed, so they become the -2 anion. Nitrogen, phosphorus, arsenic, they get their 5 valence electrons is 3 electrons removed, so they become a -3 anion. Remember that alkali metalloids tend to share electrons, so they neither give up or gain electrons. So let's take a look at common ions. These are elemental ions. It's called elemental ions because they are formed from the element. There's only one type of atom involved. Hydrogen, lithium, sodium, potassium, they tend to be +1. Magnesium, aluminum, silver, they tend to be +2. Aluminum's +3, silver's +1. And you saw that from the periodic table that I showed you earlier. Then you have your negative anions, and these are your nonmetals. Fluorine, chlorine, bromine, iodine are your monoatomic anions. -1, oxygen, -2, sulfur, -2, nitrogen, -3. And then we have something called polyatomic ions. These are atoms that are bonded together covalently, but they have a deficiency of electrons or they have an excess of electrons. And so what happens is that because they have either a deficiency, in which case they're a polyatomic cations, or an excess, in which case they're called polyatomic anions, they're going to be charged. And you just have to memorize these polyatomic ions. There's no getting around it. Get yourself a good list and write them down, because you will need to know what the formulas are, what the names are, and what the charge are for these polyatomic ions. And if you look at my website, you'll find a good list of polyatomic ions. So when these ions combine, how do we know the formula? We know the formula because we understand how many electrons a metal will give up and how many electrons a nonmetal will pick up. So if you consider potassium and fluorine, the first thing that you want to do is look at potassium in the periodic table. What you'll find is that it's in the 1A family, so its common charge is +1. That's what I have right here. Fluorine is in the 7A family. It's got 9 electrons. 7 of those 9 are valence electrons. Because it's in the 7A family, it's in the -1 anion column, and so it prefers to pick up electron. Here, now the potassium and the fluorine will combine so that you have a net neutral chemical, and that's a 1-to-1 ratio. You get potassium fluoride. So that's the formula you write when potassium and fluorine combines. You write Kf. And in fact, whenever you write an ionic compound, you always want to remember the principle of electrical neutrality. That is, the sum of the charges of the cation and the anion when you write the formula has to add up to 0. The cation charges is equal to the anion charges. And you use subscript after the elements to indicate how many of the cation and how many of the anions will give you that correct ratio so that it's electrically neutral. The best way to do this is through the crisscross method. In the crisscross method, what you want to do is you want to write down the elements that are going to make up the compound. Then you want to figure out what the common oxidation number will be. And then in this particular case, we have barium and nitrogen combining. Barium prefers to be +2, nitrogen prefers to be -3. And then we do the crisscross. The crisscross involves taking the number of the superscript for barium and making it the subscript for the anion. Taking the number of the superscript of the oxidation state of nitrogen and making it the subscript for barium. And so what we have is in this crisscross trick is Ba3, that comes from the -3 here. You just put the 3, not the negative, and 2. And this gives you an electrically neutral compound. Let me try and illustrate that in this diagram right here. When we have barium, and we know that it prefers a +2 charge, and nitrogen, and we know it prefers a -3 charge, then again we do the crisscross, and what we have is Ba3 and 2. And if we write that out, what we really have is 3 barium at +2 apiece and 2 nitrogen at -3 apiece. And if we look at the positive, this would be +6, this would be -6. You can see that it's electrically neutral. That's what we mean by electrical neutrality. Let's do another example here. In this example, we have aluminum and sulfur. In this example, we know that aluminum prefers a +3 charge. You know that because of its location in the periodic table. It's in the 3A family. Sulfur is in the 6A family, prefers a -2 charge. So if we have aluminum at +3 and sulfur at -2, and we do a crisscross, what we have is Al2S3. And what this means is that you have 2 aluminum at +3 apiece and 3 sulfur at -2 apiece. So the net is +6 and -6. Again, electrically neutral. Crisscross works because in the end you get an electrically neutral species. What happens when you write down the formula? How can you take the chemicals that combine in a chemical reaction and come up with the correct formula for an ionic compounds? Take, for example, sodium, which is written as Na, and iodine. Iodine, as found in nature, is I2. What you don't want to do is write NaI2, because that would be incorrect. The first thing that you want to do in this particular example is realize that sodium's common charge is +1 and that iodine's common charge is -1. And so what will happen is that the iodine will split up to 2 iodine ions, and then you combine the sodium and the iodine to make a formula. And so that's what we see right here. What happens is that the sodium and the iodine will combine. What will happen is that you will need 2 sodiums to combine with each of these iodines. The sodium, remember, are +1 to form NaI. And so if you want to balance this equation, what we have is 2Na plus I2 goes to 2 NaI. That's the correct formula for the sodium iodide ionic compound, and that would be the way you would write this reaction. If we take sodium and oxygen, oxygen breaks up to, let me write it up here, sodium plus oxygen, -2, -2. What you'll find out is that it will take 2 sodiums to react with the 1 oxygen. Since you have 2 oxygens here, that means that you have a total of 4 sodiums to form 2 sodium oxide. So the balance equation would be 4Na plus O2 goes to 2 Na2O. Notice that this chemical right here is electrically neutral. 2 sodiums at +1 apiece and 1 oxygen at -2. So that's how you write out these chemical reactions and how these ionic compounds form. Let me just note that there are certain chemicals out there that are diatomic. They're found in nature this way: H2, N2, O2, F2, Cl2, Br2, I2. Whenever they're referred in a chemical reaction, let's say we have a sodium and hydrogen reacting. Well, you don't write hydrogen H, you write it H2 as found in nature. Please remember these diatomic molecules. So let's summarize chemical formulas. Compounds can be formed by elements combining, and the electrons transfer occurs. When electron transfers occurs, then we have ionic compounds. When electrons are shared between 2 elements, then they could be mutually shared, in which case it's called covalent compounds, or they can be unequally shared, in which case it's called polar covalent compounds. Compounds are always electrically neutral. For ionic compounds, the principle of electrical neutrality is always obeyed. For covalent compounds, there are no charges with the element, so do not use the principle of electrical neutrality. There's no charges, and so what happens is that the electrons are being shared among the elements. Ionic compound substance will dissociate in water, that is, it will dissolve in water to form ions, and the charge of the ions will be their oxidation state. Covalent compounds stays together and generally do not dissolve in water and break apart to ions.